Hi, welcome to the University of North Dakota Multi-Omics module, where we would be using transcriptomic and epigenetic data integration. This module will walk you through some of the techniques to integrate transcriptomic and epigenetic data, for which we would be using RNA-seq and reduced representation bisulfite sequencing, also known as RRBS. Let's get started with the skills that you are expected to gain after completing this module. Some of the skills that you will gain are statistics, genomic technology, data analysis for bisulfite sequencing, RNA-seq, and integration, cloud computing, that's the Google Cloud Computing platform, some bioinformatics concepts, and multi-omics approach to integrate transcriptomic and epigenetic, and finally, data visualization. Some of the prerequisites that you expected to know before starting this module include basic command line operations, R programming, statistics and mathematics, basic understanding of omic technologies and online databases, including Geo or TCGA, and some knowledge of cloud computing environment in general. If you need to gain more knowledge about the specifically Google Cloud platform, please follow the NIH Cloud Lab README link, which will go in depth on how the Google Cloud environment works and how you can use it to analyze your data. Let's start with setting up the environment. For setting up the environment, first you would have to create a user-managed Jupyter notebook. The Jupyter notebooks could be made inside Vertex AI. The first step would be in the search bar. You can type Vertex, go to the workbench, create a new notebook, and start the R kernel. All the three modules in this particular module are developed using the R kernel. So it is important that you use the R kernel while initiating a notebook. For more in-depth knowledge on how to create notebooks using Vertex AI, please follow the King Lab laboratory link that will go further in detail on how to create the notebooks. The second step would be to clone the repository using GitHub. After cloning the repository, you will see three main folders and a README file. The three main folders include the RNA-seq, RRBS, and integration. These modules, we expect you to run them in a sequence, starting with RNA-seq as transcriptomic, bisulfite sequencing, the folder name is called RRBS, and finally the integration folder, where we would integrate the RNA-seq and reduced representation bisulfite sequencing data. The workflow or the architecture used to design this module is we start with the data from NCBI Geo, where we can directly get the data using the GSCA ID, or you can use the data that has been provided in the cloud bucket. We have subsampled the data to save on computational power. The data is then input into the cloud storage. After cloud storage, we do the basic pre-processing, which is done through Nextflow NF-core pipelines that are the RNA-seq NF-core Nextflow pipeline and the methyl-seq. These pipelines run in collaboration with the Google Life Sciences API, so it is important that you set up Nextflow and the Life Sciences API before starting the pre-processing of the data using Nextflow. To configure Nextflow with the Google Cloud Platform, we need to follow the Cloud Life Sciences tutorial. The link has been provided in the README file. Let's quickly go through this tutorial and see what it says. So the initial first step is to enable the Cloud Life Sciences compute engine and cloud storage APIs. After enabling these APIs, you need to create a storage bucket and then create a service account and add roles to that particular service account. After adding roles, you can provide credentials to your applications, and finally install and configure Nextflow in the Cloud Shell or the terminal. So after you've installed Nextflow, you can either run the command provided in each of the notebooks called RNA-seq and RRBS, or you can run these sample commands to see if it is running. Let's go back to the README file. So after we have pre-processed, we store all the pre-processed data to the output storage, that is the cloud storage buckets. And that is again extracted to the Vertex AI Jupyter notebook to perform further downstream analysis, including the multi-omics integration based on correlation tests, overlaps and enrichment co-localization, functional and pathway relation, and finally motif search. The results are then stored to the cloud storage bucket for future use. The dataset for this module has been extracted from Geo. From this particular dataset, we have chosen a subsample to reduce on computational power and to make the modules run faster. So you can use that particular subsample to run the modules. Then we have the troubleshooting guide on some of the basic errors that we came through while testing the modules. If you are experiencing any problems or errors, please refer to the troubleshooting. There are high chances you would get the answers from here. That would be all for the README file. Thank you for listening to the University of North Dakota Multi-Omics module.